Hi, welcome to my video solution on Further Pure Mathematics 3. Now, before I begin, I'd like you to take a look at this question and pause the video. Okay, so the first question is a very standard find an equation of the hyperbola in terms of x, y, a, and m. Now, we know that alpha is equal to a. Very straightforward. Setting y is equal to 0, we can see that alpha is equal to a. Now, if you've got a situation like this, then we should know that the asymptote in terms of alpha and beta is y is equal to plus or minus beta over alpha. But we are given that since y is equal to plus or minus mx, then it follows that m, and we also know that because alpha is equal to a, m is equal to beta over a. And therefore we say that beta is equal to ma. So substituting that into our equation of the hyperbola, we have here an equation of the hyperbola in terms of x, y, a, and m is given by x squared over a squared minus y squared over a squared m squared equals 1. Now at this stage, I'm going to make m squared the subject of the equation because I'll be using that later on. Okay, so just since we're here, we're going to multiply through by a squared m squared, and we're left with that expression. And we can see that if I gather the m squares to the left hand side and factor out the m squared, I'm left with that expression. And then therefore m squared is equal to y squared over x squared minus a squared. Okay, now for part B, prove that for all values of m, p lies on the curve with equation. Now we're given a point P on this hyperbola is equidistant from one of its asymptotes and the x-axis. Okay, what we're given. So what does that mean? That means that P, if I suppose that P has coordinates x1, y1, then the distance between P and the x-axis and the asymptote is the same. So those two distances, let's have a look at that again. That and that must be the same, equidistant. Okay, so part B, if I let P be any point on the hyperbola with, say, coordinates x1, y1, then because the point P is equidistant from one of its asymptotes and the x-axis, so that distance, okay, that distance has to equal to that distance, the perpendicular distance from P to the asymptote has to equal to not any distance, but in particular the perpendicular distance of P to the x-axis. That's what they mean. And we have to just prove that for all values of m, P lies on the curve with equation x squared minus y squared all squared is equal to 4x squared times x squared minus a squared. Okay, so we're now going to suppose that the line perpendicular to the asymptote, okay, joining, let's call that point Q. And let's suppose that Q has coordinates x2, y2. Well, I can see from, if I construct a small triangle, that just this property tells us that this distance squared plus this distance squared has to equal to this distance squared, yeah? Because they are equidistant, okay? So the square of the hypotenuse in this smaller right angle triangle has to equal to the square of this length here, which is y1 squared. So I can write x1 minus x2 all squared plus y2 minus y1 all squared has to equal to y1 squared. Okay, that comes from the fact that it is equidistant. Now, the equation of the line joining PQ, well, we know that because the gradient of this asymptote has gradient m, then the gradient of the normal, or rather the line perpendicular to it, the line joining the chord PQ, has to have gradient minus 1 over m. Okay, so that's important. And again, this is the usual form for the equation of a straight line. Y minus y1 is equal to mx minus x1. And therefore, and we know also that Q lies on the line with equation y equals mx. Okay, so we can work out x2 and y2 in terms of x1 and y1 by solving simultaneously. And if we did that and I substitute y equals mx into here, rearranging it to find x, that will give me x coordinate of x2. And that is a simple matter of algebraic substitution. Now we know that y equals mx, so that's very easy. So if I know x2, then y2 must simply be equal to m times x2, okay? Because y equals mx. So y2 is simply m times x2. Now the next step is to now substitute this. So these are the crucial ingredients that we have. Now we're ready to show that it satisfies the given properties. If I move this, say over here, okay. So substituting in x2 with all that into this part, and y2 into this equation, we have the following. Now here we start by combining the fractions. So if I combine the fraction, I'm timesing x1 by m squared plus 1. Okay. Now I can see that when I subtract, I can see that I have an x1 common to both of them. Okay, so this is just simply combining this fraction and this fraction. We should know how to combine fractions. And we can see that the x1s cancel out. And the m squared y1 also cancels out. Okay, so we're left with this expression. Now, the denominators are the same. But what I'm going to do before that, can you see what I'm going to do here is if I factor out m as common to both of these terms, can you see that? If I factor out m, then I'm left with this expression. Now what happens when I remove the bracket is that I have m squared times this term squared. Is that right? And of course, these two have the same denominator. So the m squared comes from the fact that when I remove the brackets, I have to square both terms. The denominators are the same. Now, what do we notice here? We notice that we have a common term, mx1 minus y1, all squared common. So I can actually factor out that as well. So let me just draw a line and factor out mx1 minus y1. Does that make sense? And here I've got m squared plus 1 on the top and m squared plus 1 all squared at the bottom. So I can see that that cancels out with one of the powers. And if I now multiply through by m squared plus 1, I'm left with this expression. Now, we can now multiply, remove the bracket at this stage. So I'll get m squared x squared minus 2m x1 y1 plus y1 squared on the left-hand side. And on the right-hand side, I'll get m squared y1 squared plus y1 squared. Now, again, we can cancel out. I can see that on the left-hand side and the right-hand side, y1 cancels out. And I'm left with this expression. And I can, of course, factor out if I bring the m squares to the same side and 2mx to that side. So just a slight correction. When we remove the bracket, we actually get 2mx1y1. Okay, so I've just made a slight correction there. And the same thing, y squares cancel out. Now, if I bring the m squared to the same side and factor it out, and I bring the 2mx1y1 to the right hand side. Now, next trick is we've got here an expression in terms of m squared. Now, this is from part A. Now, I know that m is obviously the square root of the whole thing, but what we could do here is actually to square both sides. Now, the clue is in the what we have to show. It's got a 4. Okay, so if I square both sides, I'm left with that. Okay, now I can see here. Now, why is there? Because I have an expression in terms of m squared in terms of y squared, x squared, a squared. So the trick here is I've got m here. I'd rather have an m squared. Now, if I square both sides and then divide both sides by m squared, I'm left with that. I can now substitute m squared with this expression. I'm left with this. Now, the y squareds cancel out from both sides, and if I multiply through by x1 squared minus a squared, I'm left with the answer that I was looking for. And therefore, just using this principle and substitution, we get what we are asked to show. Now, there is actually an alternative way, which is actually better. Here, if I extract this quadrilateral, I'm going to remind you of some identities from C3. Okay, the tan 2a, and therefore if a was theta, then tan of theta is 2 tan theta over 2 minus over 1 minus tan squared theta over 2. Now, we're going to call this angle theta, and therefore that angle is theta over 2. Okay, so I've just taken out this quadrilateral and said if that angle is theta, then this angle is theta over 2. Okay, so that length is the same as that length. And from this inner triangle, we can see that tan of theta over 2 is the opposite over the adjacent, which is y over x. If P has coordinates xy this time instead of x1, y1. Okay, if P has coordinates xy, then the tan of theta over 2 must be y over x, opposite over adjacent, where this whole angle is theta. Now, I'm going to express it in terms of tan theta. So tan theta, we have this identity from C3. Let me just move this out of the way. I can say, okay, substituting in tan of theta over 2 for y over x. And I can tidy that up, can't I? I can multiply through by x squared. Now, before I do that, but we know that y equals mx, asymptote. Now, tan of the angle is the gradient. Does that make sense? The change in y over the change in x is tan of the angle. So tan of the angle is actually m. So we can replace m for tan theta. Okay, so I want you to pause and have a think about that. If we know the gradient of this line is m, then we can say that tan theta is equal to m. Okay, pause and have a think about that. So now I can multiply through by x squared, and I have m is equal to 2xy over x squared minus y squared. And again, replacing, now remembering from the first question that m squared is equal to y squared over x squared minus a squared. If I square both sides, I have m squared. Substituting this in for m squared, I have that. Squaring out the brackets, and I can see that if I rearrange that, cancelling out the y's and multiplying through, I have what I need to show. So the rest is very straightforward algebra.